Hey folks, so this week's lecture is about sedimentary rocks. I had to pop this funny tweet on there since we just finished up talking about igneous rocks, where the building inspector says, "You say you've been keeping everything up to code, but your 4-year-old just informed me the floor is lava, which I don't need to tell you, it's a pretty serious safety violation." So this week we are working on understanding how sedimentary rocks form and identifying them in the lab. All right, so I know that we sort of hit on this very briefly when we talked about the rock cycle. So remember that sedimentary rocks form from sediments. And remember, sediments are fragments of other rock, right? So we can take rocks and break them up into smaller pieces, or we can take different ions in the water, put them together through chemical reactions and create a solid. And when that happens, that process is called precipitation. And so we can form sediments through the precipitation of minerals or different compounds in water. So for example, think about probably when you were kids, you made crystals out of pipe cleaners and you put them in salt water, and then overnight the salt stuck to the pipe cleaner, and then you made a pretty shiny, little pipe cleaner picture to take home. Also, when you boil water that has things dissolved in it, right, you get sort of this ring of stuff around your pot from things precipitating out. If you ever go to the beach, right, the salt water kind of sprays and precipitates, and the salt from the water gets stuck on things at the beach, right? So sediments form through this process of weathering, which physically breaks down rocks into smaller pieces, or chemically breaks down rocks through dissolution. So caves are an example of something that forms through this chemical weathering process, where the rock is actually getting dissolved by water. So no, sediments are formed through this process of weathering, where you can either physically break them down into smaller pieces or dissolve the rock through chemicals. So once we have our sediments through those two weathering processes, then they have to be transported to the location where they are ultimately going to be deposited and accumulated, right? So we have rocks breaking down, maybe they're transported in a river, or maybe they're transported by a glacier, or they're in a lake, and eventually they've reached some place where there's no more energy to carry them or transport them, and they get deposited. And when those sediments get deposited and accumulate in a place and are able to be buried and subjected to maybe a little bit of heat, compaction, then they go through that process of lithification. And so remember we said this cementation compaction process in the rock cycle, the fancy word for that is lithification, where that prefix lith means rock. So it's basically turning something into rock, is this process of lithification. And so we call it compaction and cementation because if you have larger sediments, they get cemented together, where you have large sediments that then are sort of held together by a glue, held together by a mud, sort of like the building material cement is made. So for example, these large pebbles down here that are held together by sort of the smaller, what we call matrix. So smaller muds, right? All of these larger particles are cemented together with these smaller pieces of mud. Finer sediments get compacted. So since finer sediments sort of are easier to compact into smaller and smaller spaces, and you can kind of fill up those spaces, you can compact and smush all of those particles together that are very fine, and you don't really need like a glue to hold it together like you do with the coarser sediments. So this is sort of what I was hinting at when I was talking about, okay, so we have the weathering process, the physical weathering process, and the chemical weathering process. That is breaking apart our rocks. And then they are removed from the weathering location through the process of erosion, and then are transported either on the surface in rivers or glaciers. They can be transported in groundwater, and then eventually they reach some place where transportation stops. Energy to carry them slows down, and so when there's not enough energy to carry particles, then what happens is they end up being dropped out of transportation. So they get dropped out of the river, they get precipitated out into caves as stalagmites and stalactites, and we get this process of deposition, right? So we can deposit the sediments all in one location. They start to accumulate or build up, and then that's when we can undergo that process of lithification, where you compact or cement them together. Cool. So there are different types of sedimentary rocks because scientists like to classify things. And so just like we classified the different types of minerals and the different types of igneous rocks, we can also classify the different types of sedimentary rocks. And so when we're classifying sedimentary rocks, we use their texture and their composition to put them into different groups, right? So composition would be what particles make them up and the origin of those particles, right, where they came from. And then texture is a way to describe how, right, the sedimentary rock looks. So we have three main types of sedimentary rocks. The first is clastic. Clastic rocks are the ones that form from compacted sediments. Compacted or cemented sediments. So these are the ones where you have largely those physically weathered large pieces or small pieces of rock material that are then glued together or compacted together. And those sediments, kind of another word for sediments that are physically weathered, are called clasts or grains. And so we use the word clast or the word grain to describe how big the particles in that class of sedimentary rock are. The second class of sedimentary rocks is chemical/biochemical. So we can sort of differentiate between things that are purely formed through chemical processes that don't have anything to do with life, or we can talk about how life uses chemical reactions. But we put these two in the same class. So a good example of a chemical sedimentary rock would be rock salt, which forms in salt flats from evaporation, right? So we have salts dissolved in the water evaporates away, those salts come in combination with each other and precipitate out as a solid. And then the third class of sedimentary rocks is organic. And our organic sedimentary rocks are made up of organic carbon. And so as we sort of go into this, we'll talk about how we differentiate biochemical from organic. And of course, we will have lots of practice identifying these different classifications in lab. So our clastic rocks are made up of those broken up or fragmented pieces of rock. And so the size can range anywhere from large gravel size pieces that you can easily see and hold in your hand, to sand-sized things, right? You can think of like sand grit, rubbing sand in between your fingers, and you can still see sand grains visibly with your eye, all the way down to really small particles, mud-sized particles that you can't see with your naked eye. And so we can classify clastic rocks based on how big their grains or their clasts are, how round or angular those grains or clasts are, how well sorted those grains and clasts are. So whether your rock is made up of all of the same size, right? It's made up of all sand, or maybe it's made up of mud, sand, and gravel. We can look specifically at the type of fragmented material that we have. That would be class composition. The minerals within those, the types of rocks that they originally were. And again, so here's just an example of grain size classification, where our gravel sized things and our sands are all things that we can see with our naked eye. And then our mud sized particles, our silts and our clays, are all things that we cannot see individual grains without a microscope. So here's just some examples of what sand-sized grains look like. Notice these are both examples of sandstones. They're different colors because of the minerals that make them up are different. So this sandstone's made up mostly of quartz. This sandstone has more feldspar in it. Silt-sized grains, I always think about it when you rub it in between your fingers, it feels like flour. So these are sort of the medium-sized grains that we commonly encounter in sedimentary rocks. Loess is a big thing that if you've ever been out on the plains, there's a ton of wind-blown loess. We also have some loess near any of the dune fields that we have here on the Great Lakes. They're a little farther away than the dunes because the sand in the dunes is heavy, right? So it kind of stays there. The loess is not quite as heavy, so it can blow a little farther away from the lake shore. And so we have loess deposits here in this part of the Midwest as well, which is silt-sized. And then our smallest clasts are clay sized. And so clay, think about, like modeling clay, how slick it is. So some of our sedimentary rocks, clastic sedimentary rocks, are made up of clay-sized grains. And we'll practice identifying those and sort of feeling the difference between those grain sizes, since you can't really see them without a microscope. Next, we have angularity and sphericity. So this is just how round or pointy the grains within the clastic sedimentary rock are. And so if you have really angular sediments in your rock, we call it a breccia. And a breccia is usually indicative of sediments that have not traveled far before they got deposited, accumulated, and turned into this sedimentary rock. So one example of places that we see breccias are associated with volcanic eruptions, where you have sort of the volcanic material as the breccia, or as sort of explosive events in volcanoes where pieces of the side of the volcano fly apart, right? And then they get deposited in nearby sediments, smaller, finer sediments like mud in the bottom of a lake. And then you have these angular rocks making up your larger sedimentary rock. On the other end of the angularity and sphericity debate or side of things, we have really well-rounded pebbles. So think about, right, if you've ever been to the lake shore where the pebbles there are very well rounded, or, the bottom of a creek, where water has really rounded those pebbles. They've been transported a very far distance. And so when you have a sedimentary rock made of really rounded pebbles, we call that a conglomerate. And then sorting indicates how consistent the environmental energy is. So if you have a rock that has all of the same size grains, we would call that really well sorted. And we see rocks forming in environments where there's we see well-sorted sedimentary rocks forming in environments where there's relatively uniform energy, like on a beach. So for example, on the beach, right, you have largely sand, it's the only size particle that you have. And so you can form a sandstone, which is a classic sedimentary rock made entirely of sand in that environment. If you have a really poorly sorted sedimentary rock where you have grains or clasts of all sizes, then that would be a place where you have variable energy, right? Sometimes you have lots of energy, sometimes you don't have very much energy at all. So that could be a place where a really good example is glacier transport. Glaciers are huge. They don't really care how big the particles are. They can carry really huge boulders and they can carry really teeny tiny particles. And then sort of going along with sorting is class composition. And so some minerals are more stable than others. And so the longer that the material has been transported, those unstable minerals have been lost, right? They've changed into something else, they've broken down. And so as distance of transport increases, you see more stable minerals and less unstable minerals. The less amount of transport you have, the more likely that you will have higher amounts of unstable minerals. And also, if you look at this diagram, you can see as we increase the distance of transport, we decrease in the abundance of things until eventually on a beach, all we have is quartz sand left. When in our alluvial fan, in our very variable energy environment that hasn't had very much transport yet, we have all types of things making up this deposit. All right, so that first class of sedimentary rocks is clastic. Our second class is biochemical and chemical. And so these form when we have some chemical processes that take ions that are dissolved in water and create solid particles from those ions coming together. So again, don't worry too much about the chemistry behind it, but remember, ions are either negatively or positively charged atoms, and they like negatively charged atoms like to find positively charged atoms or vice versa and combine so that they are both happy. Their outer valence is full of electrons. And water is really weird, and so it's a polar molecule, which means that it easily dissolves ions and can transport them sort of broken up as in solution, right? Sort of as a part of that liquid part of water. So think about how you have salt, which is a solid. We can put it in water and it dissolves, right? Just like completely, you can't see it anymore. And then, right, if we like leave our cup of salt water out on the counter and we let it evaporate over a couple of days, then you get, right, some salt rim form in the bottom of your glass. So this is sort of how these chemical processes happen in nature, where we have two ions coming together and they precipitate out as a solid. And so our biochemical rocks, our sediment forms through this precipitation process that are mediated or aided by the growth of organisms. Specifically, algae and coral reefs are really good examples of biochemical rocks or organisms that help build biochemical rocks. Chemical rocks, on the other hand, are not associated with organisms. They are just sort of natural, inorganic chemical precipitation that happens without the interference of organisms, right? It's just like a chemical reaction happening in the water, maybe associated with evaporation. All right, so we have two really big hitters in the biochemical sedimentary rock class. So the first is limestone. And so in the oceans, there is an abundance of calcium carbonate. So here's the chemical formula there. So there's an abundance of carbonate in the ocean, and there's so much of it that a lot of organisms in the ocean actually make their skeletons or shells up from this calcium carbonate. So the organisms are actually the ones that are taking the different pieces, right, the different ions, and putting them together to precipitate their skeleton, right? They're taking these ions in the water, putting them together, and using them to make their shells. So specifically, the two big organisms are algae. Right? So there's a lot of algae in the ocean that make up their shells from calcium carbonates, and corals, which make their harder outer sort of part out of calcium carbonate. And so limestone, the sedimentary rock, which we see a lot of in this part of the country, if you've ever been sort of fossil hunting before, is just made up of the skeletal remains of either those algae or of the actual corals themselves. The other big player in the biochemical sedimentary rock class is biochemical chert. And chert, very similarly, is made up of organisms, algae specifically, that live in the ocean, but instead of being made of calcium carbonate, it's made out of what we call opaline silica. Remember, silica is silicon and oxygen bonded together. I like chert a lot because it's made up of diatoms, which I study in my research. And we will look at chert in lab. The really cool thing about chert is that it is one of the rocks that's commonly used to make arrowheads, particularly in this part of the country where we don't have a lot of obsidian. So obsidian is the other rock that's very commonly used to make arrowheads. All right, so limestone, fun fact for trivia sometime, it'll be a trivia question in your life maybe. Limestone is the most abundantly chemically precipitated rock by far, like nothing else, none of the other chemically precipitated rocks come close. And so again, it's primarily composed of what we call calcium carbonate. And the cool thing about limestone, and one reason why that it is one of the most abundantly chemically precipitated rocks, is that we can have it created through those biochemical processes that we were just talking about, where we have like fossil remains making up the limestone, or it can also just naturally occur chemically through inorganic chemical processes where that calcium carbonate's just naturally coming together in the water column without the aid of organisms. All right, so on the flip side, chemical sedimentary rocks, again, these form through precipitation, but just chemical precipitation, just sort of chemical reactions that don't have anything to do with organisms. So we had biochemical chert, which was created of algae skeletons. We can also have a chemical version of chert, which is made up of really teeny tiny quartz grains. And so usually the silicon is derived from silica organisms, but then is dissolved or recrystallized into this microcrystalline version. Sort of more classically, and a better example, if we're going to classify chemical and biochemical rocks separately, are the class or group of chemical sedimentary rocks called evaporites, which form through the process of evaporation. So two good examples of evaporites are rock salt, which is the rock form of the mineral halite. And this crystallizes when we have evaporation of salty water. And then gypsum is another evaporite chemical sedimentary rock that also forms from evaporation of salty water, but it takes prolonged evaporation settings to form. So salt flats, for example, the Bonneville salt flats, where they do all the land speed records, and also this salt flat in Bolivia, which they filmed one of the most recent Star Wars movies at. So you can see this used to be a large lake bed. All of the water has evaporated out, and now all that's left is that rock salt halite deposit, right? And it looks like salt. I bet if you went and licked it, let's go on a field trip and go lick the Bonneville salt flats, because I bet they taste salty. And right, these are one of the locations where we classically get salt deposits. This is why, back in the day, salt was a commodity, and a very valuable commodity, right? If you think about being sort of a peasant who didn't travel very far, right? Being able to get salt from some far reach of the world would be a pretty valuable, special thing to have every once in a while. There's a couple other examples of chemical sedimentary rocks. One of those is travertine. So this is when we have that calcium carbonate, but instead of being precipitated from chemical reactions like in the ocean or associated with organisms in the ocean, we get calcium carbonate deposits from groundwater. And so travertine is a really big thing in hydrothermal places where we have groundwater that's warmed from a magma chamber underground, right? So when you warm water up, it's able to dissolve more things. That warm water reaches the surface, cools off, and then it loses the capacity to hold all of those things. And so calcium carbonate precipitates out. So if you've ever been to Yellowstone or seen pictures of the travertine terraces in Mammoth Hot Springs in Yellowstone, those are really good examples of what travertine looks like. I actually have a picture of Mammoth on my wall back there. And then Dolostone, sort of similarly, is when we have a limestone deposit that then groundwater has run through and chemically modified with some hydrothermal fluids. When we talk about groundwater, we can talk more about how these sort of hydrothermal environments work, because I think they're really interesting and special places. All right, so we have clastic sedimentary rocks, and then we have chemical/biochemical sedimentary rocks. And then our last class are organic sedimentary rocks. And so organic sedimentary rocks are made from organic carbon, which means they have carbon preserved within them, and that carbon came from a living organism. And so the hardest thing to keep clear between organic sedimentary rocks and biochemical sedimentary rocks is it's based on the actual chemical composition, where our biochemical sedimentary rocks came from living organisms, but they're largely the hard parts of the organism that have been preserved. And those hard parts don't contain carbon. Instead, right, we're focusing on how the organism took those ions and then turned it into something hard, right? So like our bones, for example, would maybe help make up a biochemically precipitated rock if we all like were put together and deposited and buried at the same time. So some examples of organic sedimentary rocks. Coal is a really good example. And so this is when we have vegetation that has been altered and fossilized, and we get a coal seam. The other thing to note, if you're having trouble sort of differentiating in your brain between biochemical and organic, is that organic, because it has this organic carbon, these are largely black or dark brown in color. And then shale is another really good example, specifically oil shale, where you have sedimentary rock shale that has a lot of organic matter preserved in it. Again, this definition just goes down to whether or not it has that carbon preserved within the rock or not, which is a hard thing to actually identify in the lab. And so when we work on our identifications in the lab, we'll sort of walk through how you figure out what class things are, and eventually identify sedimentary rocks. I personally think sedimentary rocks are the toughest to identify and get down. So not to discourage you, it's going to be fun. We're going to figure it out. We're going to learn together, right? And so, yeah, let me know what I still need to clarify about sedimentary rocks, and we can talk about that in class next week.